Good morning, everybody. Welcome to another discussion in dynamics. Without further ado, let's begin. Today, my plan is to do a very brief lecture overview, a very brief lecture review, and then two examples, 1 and 2. I think that we can cover everything. We will see, okay? But I think I am able to do all of these things in 50 minutes. And topic of today's discussion: polar coordinate system. Okay. So a little bit of info. There is a YouTube channel with recordings from our discussions. You can access it via a link from the email you got on Sunday. There is a link on Canvas, and also you can search it. Name of the channel is Dynamics for Non-Dynamicists. Okay, quick reminders, probably for the last time. Please familiarize yourself with the problem statement. The reason why you should do it is exactly the same as last time. It's for your just to save some time. It should be beneficial for you and also maybe a little bit for me. And practice makes progress, yes? So I think that this is the most important thing in this semester, actually. So I'm very sorry that I am mentioning that for the third time, but really I think that this is the most important thing for you guys. Do you want to make progress? If yes, don't use solution manuals, use this thing in here, okay? Use this thing while solving your homework. But choice is yours. Again, you are adults. Yes, I treat you like adults. Probably, I noticed that not everybody at this university treats you like adults. I decided to do it. Choice is yours. Yeah. Yeah. And if you run into some issues, just hit us up with questions. Yeah. Hit us up with questions on Piazza or office hours. Okay, I'm talking too much. Brief lecture overview or any questions? Yeah, I'm talking like obvious things. Yes. Basically, yeah, sorry. Okay, so I prepared a little bit before our discussion. Basically, you can write it down, guys, or you can take a picture maybe, or it will be available on YouTube anyway, yeah? So basically what I would like to do, I would like to compare Cartesian coordinate system, yeah, with polar coordinate system, okay? Yeah. So the story goes like that. Okay. Let us look at the left hand side. Okay. Right now. So basically, what we are doing here, we try to express the motion in Cartesian coordinate system. So the story goes like that. We have a trajectory. Okay. This thing. This is our trajectory. Yep. And we have a particle P. This particle. And that particle travels along that trajectory, okay? And we would like to know its position. So that's why we have our vector r, okay? Vector r shows us where the particle is at that time instant, okay? And there are different ways to express that vector r, okay? One of the ways is Cartesian coordinate system. And what's very characteristic about this Cartesian coordinate system are those two unit vectors, vector I, okay, and vector J. Yeah, and what's funny about them is that vector I always points in this way, always points to the right, okay, and vector J always points upwards. Doesn't matter what happens, they are always going to point in those ways. In other words, they are constant vectors. And what does it mean to be constant vector? That means that if you look at the bottom right now, if I take d dt of I will basically obtain 0, 0, 0. Yes? I will obtain 0 vector. And the same will happen if I take first time derivative of j. Okay? You saw yesterday on the lecture why it is important, yes, but I'm going to repeat it quickly today. So, because they are constant, that's why it's so easy to express those vectors when we use Cartesian coordinate system. Okay, so basically vector r is xyz, vector d is first time derivative of position, so it would be basically x dot y dot z dot, yeah, and a will be x double dot y double dot z double dot, yeah. You can use American notation here. I personally prefer this notation, yeah, vector. I prefer vector notation. Okay, they are equivalent. Okay, so that's all actually. Are there any questions when it comes to Cartesian coordinate system? Great. Okay, so now polar coordinate system, okay? So story goes like that. We are talking about exactly the same motion. Okay, that trajectory is exactly the same. Exactly the same. Okay? And basically, again, we have a trajectory that is exactly the same. We have the same particle P that goes along that trajectory, okay? And again, we have our position vector r, okay? And by the way, if you look at the board right now, we have particle P, let's say, I don't know, at time instant, I don't know, 3 seconds, okay, at this position, yeah? But let's say that our particle P at time instant 5 seconds will be here, yes? So you can see that our r will change, yes? At 5 seconds, t equals to 5, r will be here, okay? This is our r, yeah? And then, I don't know, at time instant 9 seconds, it will be here, okay? So again, our r will change in time. Our vector r changes in time. Do you see that, guys? It basically travels, yeah? Great. And now, we would like to express the same motion. I'm gonna stress it one more time. The same motion, just in a different way. We're gonna use our ur and u theta, okay? And ur is aligned with r. And by the way, let me draw it one more time. So at time and 5 seconds, our r will be here. Yes, this is our position vector. That means that our ur also will change direction. Yes, our ur will be right now in here. Do you see? So our ur is not constant. At time instant 9 seconds, r was pointing here. And again, ur will be pointing here. Yeah, ur again change direction. And direction of that ur is defined by that angle, theta, okay? Theta. So if you look at the, actually I can leave this. So if you look here, you can clearly see why ur and u theta are not constant. They change their direction, yeah? Not length, they're always unit vectors. They're always, their length is always 1. They just change the direction, okay? And that's why their first time derivative is not 0. It will be something else, yeah? In opposite to those guys, yeah? Their first time derivative was 0 because they were constant. These guys, not constant. So far, so good? Or questions? Yeah, I hope I'm using simple language to explain it. Yeah, okay. So let's get rid of all of this additional stuff. So maybe I will need some help. Can you please help me in expressing r in terms of ur and u theta? How to express ur in these terms? Anybody? It was yesterday on the lecture, by the way. Or you can just look at that drawing. Yeah, just look at the drawing. How to express r in terms of those guys? Oh, yes. Perfect. So if it is 0, I will get rid of it, okay? I'll just erase it. Perfect. Okay, yeah, that's all. This is how we express our r in terms of r theta. Okay, so now velocity is again, the definition is exactly the same. Regardless of they tell you, your definition is the same. Velocity is always first time derivative of position, okay? So that means that it will be first time derivative of that, yeah? And this is product rule, right? So that would be d dt of r, r, sorry, plus r d dt of ur, right? Okay, and so that would be r dot ur, and believe me or not, but this guy is exactly theta dot u theta. If we take first time derivative of this thing, this will be theta dot u theta. I believe that Professor Sonny showed that yesterday on the lecture, yes? But I think so, yeah? If you want to see it one more time, visit us during our office hours, okay? Our office hours, okay? So I can write in here that this is basically r u theta. So this is our velocity, okay? So our velocity expressed in this coordinate system is this. Okay, and if we take one more time derivative, maybe before taking the time derivative, I should introduce u theta, probably, yes? U theta is here. U theta is always perpendicular to ur, okay? And it's always on the left-hand side of it, yeah? It cannot be here, never, ever. It cannot be never here, okay? This is wrong. Don't put it here, okay? U theta is always on that side. And also we have theta dot suddenly appeared. Theta dot is first time derivative of that angle. That also changes. Yeah, that angle that basically defines the incline of UR. Okay, guys, that's all I actually have to say right so far. Any questions? We good? I hope I do not make things more complicated. Yeah, am I like clearing stuffs? Okay, great. Okay. And now acceleration is again the same definition. It's first time derivative of velocity, and basically, please look at your lecture notes. Okay, please look at your lecture notes how to derive it, and if you derive it correctly, you should end up with something like that, if I remember correctly: r double dot minus r theta dot squared ur plus 2r dot plus r. Yeah, you can remember that expression when you write it 1,000 times, probably, yes, or maybe less, 100 times, let's say. Yeah, so these are basically our position, velocity, and acceleration vectors expressed in polar coordinate system. And here are they expressed in Cartesian. By the way, are they the same vectors? Yes, exactly, yes. They are just expressed in a different way. These are exactly the same vectors, but expressed in a different way. Why they are exactly the same? Because the motion is exactly the same. Yes, I told you earlier. Trajectory is exactly the same, and we have exactly the same particle following our trajectory. So it's exactly the same motion. Okay, I think I'm really talking too much. Yes. Yeah. Any questions? Was it helpful? A little bit? At least a little bit, yes? Okay. Okay. Okay, guys, so I like theory, but I think that everything will be clearer if we do examples. Yeah, let's do maybe 2 examples, and everything will be even more clearer. Yeah. Okay. Yes. Example number 1. Any objections? Let's do it. Please familiarize yourself with the problem statement before we start our solution. Alrighty, so they just would like us to find velocity vector, yeah, and acceleration vector when theta is 30 degrees. This is our task, okay? So what I would like to do first, okay, let me write down, first of all, so this is how I solve those problems. I always write down those magical expressions from the previous board, okay? So let me write down them here. V, if I remember correctly, was r dot ur plus r theta dot u theta. And A was r double dot, sorry guys, minus r theta dot square plus Coriolis plus this. Okay, so we have our expressions, and we are just going to fill them out, okay? We are going to basically find r dot, r double dot, and so on, okay? We're gonna find these guys. We will find theta dot, theta double dot, and we will just plug them back in here. Okay, we'll just plug them back in here, and we will call it a day. Yeah, and this is the end of the problem. But before doing that, let us find time needed to reach 30 degrees, okay? Time t star needed to reach theta 30 degrees. Okay, so I believe I can take this expression, yeah? So basically I can take this one, 0.15 t squared, and 30 degrees is, by the way, pi over 6. Yeah, so I can put pi over 6 in here, equal to 0.15 t star squared, and our t star is equal to pi over 6, 0.15 square root, and this is 1.8683 approximately. Okay, we found our time. Now velocity. Okay, let's find velocity. Okay, so I think that to find velocity, we need r, which is here, 0.9 minus 0.12 t squared, r dot. Yeah, I'm not going even to ask you for help, okay? This is minus 0.24 t. Okay, and we also need theta dot, yeah? So let me write it down here, theta very quickly, 0.15 t squared, and theta dot is 0.3 t, okay? And now let's find their values for t star equals 1.8683 seconds. Okay, so r for that time will be approximately 0.4811. R dot will be approximately minus 0.4484. And theta will be obviously pi over 6. So 0.5236. And theta dot is approximately 0.5605. Yeah, a lot of calculator job, yeah. Okay, plug it in. And our velocity is minus 0.4481 UR plus 0.2697 U theta. Great, 50% of the problem done. We found velocity. Questions so far? We are just filling out the thing, yeah. Okay, so now acceleration. Let me copy paste this expression. And to find acceleration, we need everything. Yes, we need r, we need r dot, and we need r double dot as well. Yes. So r double dot. I'm not going to even ask you guys. Yeah, you will probably laugh at my face if I ask you for that. Yeah. 24. Okay, and we need theta dot and theta double dot. Theta double dot is 0.3. Okay. Oh, and these are exactly the value. Yeah. So these are constant values. Yes. So we can just copy paste them here. 24. Okay. What's the next step? Plug them in and grab your calculator. Yes, exactly. Plug values in. Grab calculator. Okay, if you do it, you will obtain minus 0.3911 UR plus negative 0.3583 U theta. That's it. 100% of the problem done. This is the answer. However, let's do more than 100. Okay, let's maybe draw them. Can we draw them? Okay, so let's draw our arm. Yeah. For 30 degrees, yes? For 30 degrees. We can draw our arm here. And this is our UR and U theta. UR and U theta. Okay, I'm gonna, sorry guys, I can copy paste, yeah? You, unfortunately, for those of you who are using still pen and paper, which is good, I actually really like it, pen and paper, you unfortunately must redraw it. Okay, sorry for that. I hope you don't mind. Yeah. Okay, so velocity vector. Aha, I think that velocity vector has a r component, yes, and it is negative. So it will be pointing this way. This is our 0.4481. Yes, and we have also theta component, which is positive, and it's like approximately half when it comes to length. It should be like half shorter, yes, twice shorter. So this is 0.2697. Okay, and this is our velocity vector. This is velocity of our color at this time instant. Okay, this is our velocity. Acceleration. I believe that we have negative value along the r. This will be 0.3911, and we also have a negative value along theta, yes, and it's like approximately the same length, yeah, 0.3583. Okay, and this is our acceleration vector. It's our acceleration vector here. A. Yeah, so this is what velocity our color experiences and what acceleration our color experiences at this time instant. Questions? Is it a little bit abstract what we are doing here, or is it okay, guys? How does it look like from your perspective? Yeah. By the way, if we solve that problem in Cartesian coordinate system, how those vectors will look like? If we solve that problem in Cartesian coordinate system. Yes, exactly, because it's the same motion. Exactly. And you again. Okay. Okay, guys, that's it when it comes to example number 1. Any questions? Yeah. Maybe something I forgot to do at the very beginning. So this is our this is our equation of motion. Because basically in here we just would like to describe the in this course we would like to describe the motion, yes? So you can guys maybe tell me how that motion of that color would look like. So first of all, theta goes this way or this way based on this. Yes, perfect. And color goes farther from point Q or closer to point Q based on this. Yes, closer, exactly. Yeah, because the distance. Yes, so it's like a spiral. Yes, and color will come closer and closer to point Q. Yes, it will be like a spiral. Yeah. In general, it will be a spiral. Yeah, but at this time instant, these are our velocity. This is our velocity and acceleration. That's at this time instant. Yes.
Is theta always in radians usually? So like, how can we change the pi respective to these?
Yeah, quick answer, use radians only, always, okay, unless specified differently, okay? In this, so physically it is in radians, yes. It is in radians, yes. Yeah. To be on the safe side, you use it in radians only, yeah.
Okay.
Are we satisfied with my answer?
Yeah.
Okay. Any other question? How we are doing with time? Great, okay. It will be quick discussion, guys, because this is also a quick problem. So what? Please familiarize yourself with the problem statement before we start our solution. Yeah. You can also write in here, omega is also constant. Okay, so I'm just gonna write down our magical expression from the first board or second board. A is r double dot minus that. Okay, so this is general expression for our acceleration, yes? This is what we have in general. But we can simplify it for that problem. For example, you guys maybe can tell me what is theta double dot? 0. And why? Because omega is constant. I heard you, yeah. Omega is constant. Exactly. And also the same thing for r double dot. This is also 0, and for the same reason, yes, because v is constant. Yeah, and in this, actually, wait a second. R double dot, R dot is constant, I mean. Yeah, and they told us that R dot is like V, basically. But it's only in this example. I should switch it. Okay, you know what? Let's not use V in here. Can we use, let's use W, okay? Or not W, let's use U also not. Give me a good letter. R dot, basically, okay? R dot. R dot, okay? Because V is reserved for magnitude of the entire vector. Yeah, so sorry guys for that. Okay, so basically this is 0 and this is 0, yeah, thank you. So this is 0 and this is 0. And we have A is equal to minus R theta dot square UR plus 2R theta U theta. Alrighty, so this is lateral acceleration. And magnitude of that, that's operating magnitudes. G simulated will be equal to, so G sim is R theta squared. Okay, and that problem is basically very quick. So right now we just have to, and so let me write down this also. A lateral is equal to 2R dot theta dot. Okay, so we have our two expressions, yes? And now they told us that simulated gravity should be larger than G2, yeah? If you look at the problem statement. So we should have R theta dot squared larger than G2. And they also told us that A lateral should be smaller than G divided by 20. So we now have 2 R dot theta dot smaller than G20. Okay? Maybe let's also plug in values that they want us to use. So instead of theta dot, I will use omega, okay? Omega is theta dot. So I can plug in those values here. I can get rid of that. I can put omega instead of that. Okay, so what do we have in here? Maybe let's focus on the second expression. This expression. We know that omega is smaller than G divided by 40 R dot, yes? And R dot was constant, R dot was 2. So basically our omega is smaller than G over 80. And this is one of our requirements. We found the requirement for omega. And this is what they are actually asked us for. We are getting closer to the solution because they ask us to find the ranges of suitable spin and radius. Okay, so we already found a range for our omega. We found a range for our suitable spin. Okay, and when it comes to R, we can use this. I forgot squaring here. Yeah, sorry guys, my mistake. Squaring here. Yeah. So R is larger than G divided by 2 omega squared. So these are our two requirements. Two requirements. To model our space station. Let's maybe plot them. Let's plot these two functions on this plot. On this axis, I would like to have R. And on this axis, I would like to have omega. Yep. First of all, they told us that omega must be smaller than G over 80, of course. Yeah. So omega must be smaller than that. And also, R must be larger than this function, I believe. This is how that function looks like. Yeah? It's like kind of hyperbolic function, yeah? So this guy is G divided by 2 omega squared. Yeah, correct me if I'm wrong. I think this is how that function looks like. Yeah. Okay, and this is our suitable range. Yeah, because we have to be larger than that function, but smaller than this vertical line. Yes. So this is our answer. Suitable range for R omega. Yeah, R and omega. Yeah, this is our answer. Yeah, I think I went too fast. Yeah, at the beginning. Yeah, because I didn't specify what they ask us to do. Yeah, I said some of you are writing. I'm just gonna scroll up for a second. Okay, so this is exactly what they ask us to find. Determine the range for sputables omega and R. Yeah, exactly this is what they're asking us for. By the way, let's have like as smallest space station as possible. Okay. So where is the smallest radius on that plot? Yeah, this is actually omega. This is value for omega. Yeah, but in that corner. Yes. Yeah. So this is basically the smallest radius. Yes. This will be R mean. Okay. Let's design the smallest space station possible. Okay. So R mean is approximately G divided by 2 omega squared, but omega must be G divided by 80. Yes, let's plug that value in. G divided by 2 G squared divided by 80 squared. So this is exactly 32,000 divided by G. Are we in SI units or US units? We are in SI units. So G is 9.81. And if you grab your calculators, this will be approximately 3 to 6.198 meters. And G for that, and and omega max in that case, yeah, will be 9.81 divided by 80, which is 0.1226 radians per second. Or if you prefer RPMs, this will be approximately 0.171 RPMs. Questions? Okay, guys, the most important part of today was actually a lecture overview, okay? Do you understand the concept of rotating coordinate system? The coordinate system that follows our particle, yes? These guys don't care, yeah? They always point in the same direction, yeah? These guys follow our particle, yes? Follow the position vector. And then so this is theory, now how to use it. Take the expression from your cheat sheet. Yeah, we will give you like the equation sheet, yes, on the exam. Take those guys, fill them out. That's all. Yeah. Any questions? Yeah. Okay. You are dismissed. Thank you, everybody. Have a nice afternoon.